Good afternoon. Now I'm going to talk about using the simulation tools to check out an AC circuit in MultiSim. So I've got the circuit over here. You can see that it still has a DC source. I've put in a capacitor, which is an AC component, but I still got a DC voltage source in here. So what I'm going to do is I'm going to take that out and I'm going to replace it with a function generator. I usually and I can take this guy, I can flip him horizontally, because I usually like to have the positive side. This function generator has a positive and a negative output, and I usually like to have the positive side going to my circuit. It doesn't really make any difference. It just kind of makes me feel better. And then I'll ground the common terminal here, and now I'm applying a voltage source into the circuit. Double click on this. And now I can set the voltage source. So right now it's a sine wave. You can also do triangle or square waves. So it's a sine wave. We'll make it 1 kilohertz. And it will be 10 volts peak with a 0 offset. So 10 volts peak means it's plus or minus 10 volts at 1 kilohertz. So here so that's putting down the generator. I can put down one of these probes over here, increase the font so we can see it a little bit better. So here I put down a probe, so I'm measuring the voltage at that point. I press the simulation run, and here I can see that the volts is it's jumping back and forth between a couple of millivolts. So it is an AC waveform, so it should have a very low average DC voltage. This guy is not actually measuring that very well. The peak to peak is 1.05. Not doing that very well. So perhaps the probe isn't really the best tool for an AC circuit. Let me try the voltmeter. Here's the voltmeter. We'll make it volts, AC. Run the simulation. So it's a lot more stable now on the AC voltage, 371 millivolts. And it's going to be pretty small depending on frequency. And we have that here in the probe. It says it's 372 millivolts. RMS, that's the AC voltage. The frequency is 1 kilohertz. The DC is in a microvolts, very small. So this first one here at the top is just jumping around. So here the probe is not doing great on the average voltage and the peak to peak, but it's doing pretty good on the rest of them. Maybe what I'll do is I've taken out a thing. I want to connect this point to this point. So if I go with a Control J, I can put down a junction, and then I can add in a connection between those 2 points. Now the meter will show me a AC waveform. It shows me the voltages. It doesn't show me the shape. So what I'm going to do is I take this meter out, and I'm going to insert, if I go up to these tools, there's a watt meter. Here's an oscilloscope. Usually when I'm using an oscilloscope, I will put channel 1, channel A, on the input, and channel 2 on the output. And let's ground both of these terminals. So A is on the input, B is on the output, and then when I get the scope going, I can compare the 2 voltages to each other. If I double click on it, it pops up a window for the scope. The black screen is kind of hard to see, so I can reverse that over here if I click this button. So when it starts running, it'll go to white. So here we go. I'm going to run the simulation. Reverse it, it's red channels on white. So this is a two-channel oscilloscope. And channel A, what I like to do usually is put channel A at the top of the screen so I can reposition it with the position dial here. You can also type in a value. I want that at 1.5, which would be exactly in the center in the top half. And then here's the output. I can type in minus 1.5, and that will be exactly in the center on the bottom. I can change the volts per division, making the bottom a little bit bigger. And I can also change the seconds per division, the horizontal axis, so I can see a little bit more. I've always kind of had a little bit of problem with the triggering on these scopes. It seems to be a little wonky, so play with the triggering. So here I've managed to get the triggering. Can also stop the simulation, and you can see on the input here I've got 20 volts per division, so the input is 20 volts peak to peak, which is what I set here. It's 10 volts peak, which is 20 volts peak to peak. So that's the input, and then the output looks like it's about 2 volts per division. So there's 2 plus maybe a half, might be about 3 volts peak to peak. So here I can monitor the input, here I can monitor the output. I can also grab these scope bars here, and I can look at them at points in time. So here at this point in time, channel A is 10 volts. That's the second probe. So at this point in time, so I got the first probe number 1 basically lined up with that peak. So that ends up being 10 volts peak for channel A, that is the input. And at that point in time, channel B is at about 0.5 volts. So the input is 10 volts peak. The output, if I put it right on a peak here, if I put that right on a peak, I can see that the output is about 1.5 volts peak, so about 3 volts peak to peak. You can also measure the phase shift here, but it's a little tricky. So this is how you use an oscilloscope. Sometimes if I am crowded for space on a schematic, what I'll do is I'll move the oscilloscope over here to the side, and I can place connectors. So I can place an on-page connector. I can call that one input. And I can place another on-page connector. I'll call that one out. Like so. Take this, copy it. Take this guy, copy it. Control C, Control V. Rotate, rotate. Let's connect that to there. Rotate, rotate. Take that guy to there. But you got to make sure they're the same name. So I'm going to make that input, apply. So that is input, so that is connected to that point. Although the wire is not there, there is a connection there. And here's the output. Apply. Turn that on. Run the simulation, you can see that it still works. So sometimes if I'm trying to monitor a whole bunch of points, if you're trying to monitor a whole bunch of points, there's also a 4-channel oscilloscope. But I find when you put it down, you got wires everywhere. And it gets kind of, the circuit itself gets lost in the noise and what you're looking at. So with something like this, I think dragging it over to the corner and just doing on-page connectors to connect it to those points. Makes it a lot easier to see what's going on. This guy here, a little different. So let's start simulation here. There isn't enough buttons to have separate buttons for every channel. So what you do with this one is you go to channel A here, and then you set channel A. So there's channel A. Move it up. And then I go to B here, and I adjust settings for channel B. So you adjust the settings for the channels independently in order to test the circuit. Stop that for a second, delete those guys, get it running again here. Let's try it with a probe. Power, voltage difference, voltage and current. So I'm going to put a voltage probe down here. Okay, so I can't see, one of the things I can't see with this one is I can't see what the phase shift in the circuit is, because the function generator, although it's a sine wave source, it doesn't have a phase associated with it. So what I can do is I can stop the circuit, and instead of a function generator, I can go over here to my sources, and here it says place AC power source. So now I'm going to put down one of these guys here. So this doesn't look like a nice instrument, but it's really doing the same thing. It's supplying an AC voltage. So let's make it 10 volts. This is RMS voltage now. So we'll do that, apply 10 volts RMS. But this one, it's 60 hertz, and it says it has a 0-degree phase shift. So this guy is the 0 degrees. This guy is the reference voltage, and any phase shifts or shift in the sine wave will be in reference to that one. I'll make it 200 hertz. You can type in the values, run the simulation. It's not showing me phase shift. It's showing me the frequency. Let's try one thing here. So that's how you would do AC. Let's go back to my original circuit here. You can only run simulation on one circuit at a time. So if you want to switch, you got to turn the simulation off. I'm going to put a AC source here. And we'll make that 20 volts. So here I get an AC source on this side, a DC source on this side. These points in the middle are going to have some AC in them, and they're going to have some DC in them. So if I drop down the probe here, so this point here is 10 volts DC, so that's the DC average voltage, but it's also 10.3 volts RMS. So this probe will measure the AC component and the DC component at the same time, and sometimes that's pretty handy. Okay, so I'm going to show you in the next video, I'm going to show you how to do this, use simulation tools with a logic circuit.